I have updated the website. If you look at the schedule, you can see that homework 5 is due Monday next week. Okay. This is the first time you have to work hard in this class in the semester. Yeah. Homework 6 is about the calculations and maybe a little bit simulation, I forgot. But all these diodes and pin junctions calculations, very simple. And next Friday, midterm exam will be in here, 55 minutes just in class. I'll give you a quick review on Monday next week. Good news is it's Friday today. A piece of silicon, I just put some phosphorus on the top and then place everything into the furnace. So the material, because of the concentration gradient, because you'll have more phosphorus here and none of them here, so it's going to diffuse into the silicon. Right? So this silicon becomes a doped silicon. So every phosphorus atom is going to bring one free electron to the silicon. Intrinsic, extrinsic. So this is just a pure silicon. This is a doped silicon. So if the concentration of this donor, that's a electron donor, that's a concentration of the electron donor. So the unit is the number per cubic centimeter, like whatever here, right? Per cubic centimeter. If this is given, and because this is being doped by this material, and this number is usually way larger than the concentration of the free electrons in the silicon at the very beginning of the intrinsic silicon. And what is that? Ni, right? Remember Ni? At room temperature, which is 25 Celsius in the US. In somewhere else is different. Depends on if you have that funding to support that heater system in the room, right? But room temperature in the US is 25 Celsius degree, which is amazing. I mean, it's pretty much everywhere. If you get into the building, it's a room temp. It didn't happen to me when I was in school in China. So in the summer, it's just super hot. Like whatever outside the temperature is going to be the same temperature inside. And if you sit on the, so when I was preparing for my graduate school, we have to, sit in that type of classroom for 6 months, just preparing for that entry exam. So it's called GRE in the US, but it's 10 times harder in China to pass that exam. And you have to take that 6 months effort to do it. So it's a lot harder over there. In that situation, you sit on the, it's not like these soft chairs, they're just pure wood chairs. And you sit on that chair, it's not ventilating really well. Your pants just getting wetted after 1 hour, but you have to sit in there for 10 hours every day. And after lunch, usually the restaurant on campus are way better than here. And so it's like $1 US, you can have a full meal, fantastic Chinese food. So everyone gets super full after lunch. So lunch coma happens to everyone. So there's a lunch break. It's after lunch break. There's another nap break in China for all, not just China. I think for Asian, Japanese, Korean, Taiwan, China, it's a mandatory break after lunch. Usually they start working at 2 p.m. So there's no chance there are some classes scheduled at 12 p.m. or 12:10. No, never. Everyone is in nap. They're sleeping. I was thinking like, why? I was not used to this because I have to work continuously from usually 8 a.m. to sometimes 4 p.m., 5 p.m. I'll just go home. But over there, they start working at 7 a.m. and 12 p.m. will be lunchtime, and I have to break for two hours. So start working at 2 p.m. every day. And it's a very formal sleep actually, 2 hours. I was thinking probably because the lunch is just too formal. It's just eat too much during lunch. So Ni in room temperature is, I can't remember the number, like 1.5 times 10 to the 10th. This many electrons or holes in the intrinsic silicon. So room temperature, 25 Celsius or 300 Kelvin. They are both room temperature. And if we know this one, if we know this, if this number is given, because this number is going to dominate, it's a donor atom concentration, and every atom contribute 1 electron here. So it's going to be very close to the electron concentration, which is N, right? Definitely N. But for the subscription, so what's this going to be? If it's a donor, electron donor, phosphorus here, so how should I denote this? So the electron concentration in here should be N, and N here, that's N type, and this is the electron concentration. So this can be considered as this number in the N-type semiconductor. And because we know that no matter it's intrinsic or extrinsic, N times P equals to Ni squared. That's a conclusion from physics. And this also applies to this phosphorus doped silicon, piece of silicon. So N is an electron concentration, and here it's NN, and it's given because Na and Nd, the donor concentration Nd equals to Nn, and that's why we know Nn here, times P. It's an N type with concentration of the holes, so that's why it's written as Pn. So here is always a type, material type, it's N type, the concentration of the electrons, concentration of the holes. And this also equals to this, and this is given because this is a concentration of free electrons in the room temperature for intrinsic silicon. It's always this number per cubic centimeter. So we can calculate for the concentration of the holes, which is Ni squared over Nn from here, and which is also Ni squared over Nd, which is given. You can calculate for the concentration of the holes. Is that clear? The same for the p-type. So this is n-type. So it's n-type because n usually reminds you about the negative, right? Negative or electrons. So you have more free electrons in here for the n-type. That's why usually we use a phosphorus as a dopant for the silicon, so you can get an n-type semiconductor. And for the p-type, which has extra free holes, is being doped by boron. And for boron, every boron carries one free hole, right? That's why every hole is an acceptor for the free electrons, because the holes accept electrons or being neutralized by electrons. And A means acceptor. That's the concentration of the acceptor atom. Atoms. So if you have this much donor items in there, we can consider that you'll have this many free holes in the doped silicon because this number just dominates. There might be 1.5 times 10 to the 10s that many free holes in there at the very beginning for the intrinsic silicon. However, usually this number is way larger than that. Think about that. If I have this number equals to 1.5 times 10 to the 17, you can just ignore this one, right? It's just too small, ignorable. Just ignore it. So this number equals to what? Use the same rules here. So how do I want to write it? This number equals to what? The concentration of the holes in the p-type semiconductor is very close to this number. Okay, and given that n times p equals to ni squared, that's how you can get these connected, right? It's a conclusion from physics. So this is how you can get everything connected. That's the intrinsic, so node doped silicon concentration square equals to n times p, no matter it's intrinsic or extrinsic, doesn't matter. So now we know that P times what equals to ni squared, given that conclusion here. P is the concentration of the holes. PP times what equals to ni squared. Same rules. N times Pn is ni squared in the n-type silicon. And here for the p-type silicon, it's PP and what? ND. It's a p-type. So in here, what is the majority? What's the minority? The holes are the majority and the electrons are minorities. Sorry. Here, electrons are majorities and holes are minorities. N-type. For p-type, let's do some calculations for this example. N-type silicon and dopant concentration is ND 10 to the 17th per cubic centimeter. So find electron and hole concentrations at room temp. And T equals to 300 K. n-type. Makes sense because that's a donor, electron donor. Okay, so Nd equals to what? NPPN, NP. What is that? Nd equals to what? PP? NP? NN? And use the equation NN times what equals to NI squared, and NI is given. Huh? PN. So first, so the question here is find the electron hole concentration. So what's the electron concentration? Do you know that before we do any calculation? So that's the electron concentration in the n-type. So directly the Nd is given already, right? So the electron is 10 to the 17th per cubic centimeter. And now let's calculate for Pn, which is Ni squared over Nn, which is Ni squared over Nd, which is 1.5 times 10 to the 10th square, right? Over 10 to the 17th, which is 2.25 times 10 to the what? $83, 13. Is that 20? So minus 17. So that's a minority. You're gonna have 2,000. Only 2,000 holes. Oh my goodness. Another example. So that's the concentration of the holes, right? Wait, I actually don't have another example for you guys. Fine. So I'm gonna just move forward. There's a concept called drift current. If I got a piece of silicon and I apply a voltage to it, it's intrinsic silicon. It's not an insulator, but it's not a conductor as well. So it's a semiconductor. So there will be a very, very weak current flow through this piece of silicon. And so the electric field is called E as the intensity of the electric field. And there will be, so if I do this, then the holes are going to move in that direction or drift in that direction. And electrons, it's going to move in that direction. Since these particles are moving, there will be a velocity associated with the movement. So V holes drift equals to mu P times E, and that's the mobility of the holes. And that's the electric field intensity. Same for the electrons. That's Vn drift equals to mu n times E. And once you guys know that mu n is larger than mu p, which means electrons move faster or easier than holes. So that's why the same size of the PMOS has a weaker, oh no, so the same size of the PMOS is weaker compared to the same size of the NMOS. The size means the width, usually. If you use the same lens for each of the device, then same length, same width for the PMOS and NMOS, and the PMOS will be weaker. So how do you know it's weaker? And where can you tell it's weaker? Remember I did the inverter simulation last time? So if I use the same size for the PMOS and NMOS, then the switching point will be less than 2.5 or larger than 2.5. So if I use the same size for PMOS and NMOS, so which is stronger? NMOS is stronger, right? So if NMOS is stronger than 2.5, so the switching point will be less than 2.5 or larger than 2.5. Think about that, right? So here, so 2.5 is here or here? Here, right? Why? Here's 2.5. No, it's exaggerated, but 2.5 is somewhere here probably. Why? It's pulling to 0 earlier, right? Earlier than 2.5. Okay, good to understand that. Resistivity is rho equals to 1 over Q mu P times P plus mu N times N. That's a piece of silicon, right? It's going to have a resistance. So that's the resistivity. So how to calculate the resistance from resistivity, remember? It's rho times what? I got a piece of wire, a rod, L over A. So L is the length, A is the cross-sectional area, and times the resistivity will be the resistance of the material. So that's why when you are doing the layout, you don't want to make the polysilicon too long. Because polysilicon is not metal. Usually they will deposit, it's called silicide, something more conductive on the top of the polysilicon to make it more conductive. But however, it's still not metal. So you don't want to use too much of polysilicon for the connections. You want to use metal. So whenever you feel like it's going to have a long distance between this node to the other node, you're going to drill a hole to the top layer to get a metal one to run the trace, and then drill a hole down to polysilicon instead of using pure polysilicon all the time. Because of the L is on the top, right? Longer L, larger L will give you a larger resistance. So here's a equation to calculate the resistivity for this material. And another parameter is called conductivity. It's just the reciprocal of the resistivity is 1 over rho. So Q here, which is introduced to the mobility of the holes, mobility of the electrons, the concentration of the holes, concentration of the electrons, right? And Q here, so Q is the magnitude of electron charge. So the unit for this is coulomb. C. So one single electron carries this much charge. (1.6 times 10 to the negative 19 is cool. Example. Given P equals to N equals to 1.9 equals to 1.5 times 10 to the tens per cubic centimeter, and mu N is 1350 square centimeter per V times S. And mu P equals 480 square centimeter per Vs. Voltage times time, so voltage time, right? You can tell N is larger than P. So what is the resistivity? Rho here, what is rho? So we know that rho equals to 1 over Q mu N times N plus mu P times P. And you can just plug in all these numbers. Q is 1.6 times 10 to the negative 19. Cool, right? Cool. Times. Is that Coulomb, or how to pronounce that? Did you learn that in physics? Will they just say cool or Coulomb? Never say cool, right? Okay, sorry. That's a Chinese translation. It's not always good to learn another second language. 1.6 times this, mu N times I won't put the unit in there because I'm running out of space. 480 times, it's intrinsic silicon, right? So the result, I'll just let you know the result in case you are trying to calculate it. This is 2.28 times 10 to the fifth, sorry, not 15th, fifth. So what's the unit here should be? What's the unit of resistivity? So look at here. So this one is centimeter, and this one is square centimeter. So you are getting a 1 over centimeter, and eventually this is ohms. So rho equals to ohms over centimeter. Is that correct? Oh no, ohms times centimeter. Right? So that's the unit for resistivity. Ohms times centimeter. It's a unit. I'll give you 20 minutes for the quiz, to do the quiz, all right? So start doing that 11:50. They got 6 minutes. One more example to burn that 6 minutes. P-type and Na equals to 10 to the 16th per cubic centimeter. and mu n is 1110 mu p is 400 centimeter square per V times S. So just to write down the equation first. So now let's check what do we have and what we don't have. Given, NA is what? NA is which? P. So now you need to know to calculate this first. How to calculate it? N equals to what in here? That's the N type or P type? P type, because it's given, right? Or you can tell from here is acceptor is a majority here. So it's a P type and N equals to Ni square over P, and P here in this P-type semiconductor is PP. And PP in a P-type semiconductor equals to Na. So N eventually equals to 1.5 times 10 to the 10th per cubic centimeter square over 10 to the 16th per cubic centimeter. And the result is 2.25 times to the fourth. Right? So now you get N, and you literally have everything to get this calculated. Pretty simple, right? So what's the result? I'll let you calculate it if you like. I think I will just stop here. I won't cover too much regarding semiconductors because this is not an analog class. But since you haven't been analog, it's going to be difficult to understand the substrates and layouts. It's better to run through this first. So we are not able to finish everything today. And we'll probably use next week to cover all these basics. Okay.